So we're now going to talk about position synthesis using superposition. And you might see the graphic up here. It looks a whole lot like M and K circles. Well, that is what we're going to use for our approach here, is overlaying M and K circle solutions for two different three-precision position problems. So we'll talk a little bit about how we do this and why we do it, and then how we go through the solution technique. So let me start off here with the M and K circle example that we've had thus far, which is looking at the cover of the headlight, and say, let me extend this three-position problem out by adding an additional precision position. So you'll notice I have labels of 1, 2, and 3, or positions 1, 2, and 3 here. I'm going to add another position that is between 2 and 3. I'll call that position 3, and I'll rename 3, 4. So here was our previous solution for M and K circles for a given beta 2 free choice. I'm going to add this additional intermediate position, which might partially block the headlight, and this will be, or perhaps a guiding position. This will be our additional precision position, and now we're going to superimpose two different problems. So I'm going to solve two different three-precision position problems. First of all, using positions 1, 2, and 3, and then positions 1, 2, and 4. By superimposing those, I can then find where do I get solutions for both, and that will then allow me to have a solution that goes through all four precision positions. So that's my approach. Where we're going to start is by using all the poles that we had generated previously. So remember that I had generated poles P12, P13, and P23, and then used pole P23 to find the image pole P23 prime, and I did the same thing then for using position 4. Now, I'm assuming that you can find all these poles, so therefore I've just thrown them on the screen for you. I'm going to use these poles now to solve for basically M circles, and then say where my M circles overlap for these two different three-precision position cases. Those will be solutions that are valid for both, or for all four precision positions. So I've got my poles, and now let me start to generate my M circles. Now we remember that our M circle touches pole P13 as well as pole 23. So let me start sketching this in here. So I've got 1, 3, and 2, 3. I'm going to first of all generate that line of centers, and the way I would do this typically is to do a perpendicular bisector between pole P13 and 2, 3. Let's see if I can get that a little bit closer. 1, 3, and 2, 3. This is my perpendicular bisector between the two of them. And then I can say, for a given choice of beta 2, let me pick the same one that I had previously, which I believe was minus 110 degrees. For that free choice of beta 2, now let me sketch in, so there's my center. Here is the 110 degrees, so I'm going from pole 1, 3 to the center of the M circle 1 to 2, 3. So that tells me that this angle right here, this will be beta 2. And it is a negative angle, therefore it is a clockwise rotation. So that tells me then where the center of M circle 1 is located. I'll do the same thing for a second M circle, so that's why I'll call this one 1. And then I can sketch in my first M circle. I'm going to do this now again for positions 1, 2, and 4. So I will create a perpendicular bisector, and this is bisecting 1, 4, and 2, 4. So I've got 1, 4 right here, 2, 4 right here. This is my perpendicular bisector between the two of those. I again will use the same free choice of beta 2 because positions 1 and 2 are in both subproblems, so I have to use that same free choice of minus 110 degrees. And then that will define this angle right here, beta 2. And I can then use that to say, here is the center of my second M circle, CM2, and draw my second M circle. So we have now generated two different M circles for two different three-precision position problems. But because they all carry positions 1 and 2, and the only difference is position 3 and 4, if I use the intersection of these two M circles, which are either this position, this position right here, or this position down here, if I pick either one of those intersections, what that'll do for me is that'll allow me to place a ground pivot that satisfies all four precision positions. So you'll notice that for a given free choice of beta 2, I have two different solutions. And I always have two different solutions unless my two circles do not intersect, in which case I do not have any solution. So I always get 0 or 2 real solutions for a given free choice of beta 2. Now, I'm going to get into a demo here of this in just a moment, but one thing I want you to think about is what happens as I change my free choice of beta 2. That beta 2 free choice really scales where the center of my M circle is, and therefore what the diameter of my M circle is. And you can imagine that as I start to scale these, I'm going to be able to connect the dots, and for a variety of beta 2 free choices, I can have a variety of solutions. Well, as these beta 2 free choices start to connect and I look at where these ground pivots lie on the plane, we're going to form Burmester curves. And this is then what we will find analytically using our complex number approach. So, very powerful tool. What I now want to do is take my precision positions that I have measured off here, and again, all 4 precision positions happen to be horizontal and therefore have no imaginary components. So I have measured off my displacement vectors, delta 2, 3, and 4, and these should be vectors, so I apologize for that. And then I've measured the alpha angles, which is the rotation of the coupler from the first position to the second, first to the third, first to the fourth. I'm going to plug these now into MATLAB, and we're going to generate these 2 different M and K circles. Notice I only did M thus far to keep it from getting too complicated and overlaying too many. We'll look at how these solutions vary as I start to make free choices. So here we now are in the MATLAB code, and what I have in MATLAB is the displacement vectors and the alpha angles that I had previously prescribed, alpha 2, 3, and 4, delta 2, 3, and 4. And again, as I had mentioned, this is a 3 precision position code, but I'm running it twice. And so I've got a beta 2 free choice, and this is minus 110 degrees, just like I did graphically. Outer loops, remember previously I was using the outer loops to iterate through beta 2s. In this case, I'm only going to fix beta 2 to 1 value. And then I can have inner loops. In this case, I'm going to generate 500 different values of beta 3, so I'll create fairly solid circles for my M and my K circles. Then as I move into my actual solution loop, you'll notice that I create a coefficient matrix, a product matrix, and then solve for W and Z. And because I'm doing this for 2 different problems, I call this W1 and Z1. I then do the same thing over again for positions 1, 2, and 4, coefficient matrix, product matrix, solve for W and Z. And then I go ahead and print this. So I'm going to go ahead and run this code, and then we'll talk about the solutions. So here I have the solution that MATLAB just printed out for me. And you'll notice that I've tried to color code these such that the M circles are blue and cyan, and the K circles are red and magenta. So my intersections between the two, just like we saw when we did this graphically, I get an intersection right here, which is a valid ground pivot, and I get another valid ground pivot right here. Now I would have to go through the full M and K circle construction where I run the rays and use the angles to figure out what are the corresponding K pivots that are associated with these. But I have played with this before, and I know that this happens to be the moving pivot for that solution right there. So then this would form out to the precision point right here. And if I wanted to use these 2 different solutions to generate a 4-bar, I could then also use this other location of the 2 K circle intersections and have this as my entire 4-bar of my mechanism. So that would then be the coupler right here going out to precision position 1. And I should find that as I go to position 2, I get minus 110 degrees rotation, so clockwise rotation of 110 degrees for both of these links, both input links as I go from position 1 to 2. They're going to have different values to beta 3 and for beta 3 and beta 4. So now I have a solution for this. Now start to think about iterating through different free choices of beta 2. And as the diameter of these circles grow, and as, because their line of centers are slightly different, I'm going to start creating curves in space. Now, these curves in space are what we call Burmester curves. So these Burmester curves are what we call the loci of solutions, but Burmester curves are really going to be very useful for us in defining where our pivots will be, our ground pivots and our moving pivots. And we're going to find that any free choice of beta 2 will give me 2 different solutions, or 0 solutions if I happen to have cases where my circles, in this case, do not intersect. So we're going to find that using M and K circles, I can identify if I have 0 or 2 solutions. And then when we go to complex numbers, we're going to also be able to identify whether or not I have 0 or 2 solutions based on whether or not there's a real or imaginary solution for the nonlinear system of equations.